I'm happy to welcome the second speaker, Georg Martius. He got his first degree in Leipzig, then his PhD in Göttingen, and then he was postdoc in Austria and Germany, correct me if I'm wrong. And right now he's leading the research group on autonomous learning at the Max Planck Institute for Intelligent Systems in Tübingen in Germany. And today he's going to talk about towards model-based reinforcement learning on real robots. So the floor is yours.
Thank you so much. I'm really happy to be here. Thanks for the invitation. It's great to speak in person again. Let's see how I manage today. So this is a great audience here. So yes, so I'm at the Max Planck Institute for Intelligent Systems in Tübingen. And the vision of my research is to develop dexterous and versatile robots as assistants for humans, for instance, in collaborative assembly tasks or in tackling global challenges like planting trees and so on, or in construction, or for instance, in taking care of people, right? And so if you want robots to be successful in all of these tasks, we need ideally that they can learn to become better and better, be adaptive, and also be safe. And so reinforcement learning is the domain where we have seen great successes in getting to learning to control systems, and recent years have shown remarkable achievements, for instance, in robotics, in this in-hand manipulation shown here on the top of this cube, or in defeating human players in games like, board games like Go, or computer games like Dota and StarCraft. So far, these results are really cool, but they are done in simulations, and they need prohibitive amounts of data and a very long time to train. So this in-hand manipulation was about 100 years of simulated interaction time. So the current situation in field robotics is that we have hand-tuned controllers, but in research we are seeing more and more increasingly how learning strategies are used, and the predominant strategy at the moment is using simulations of the robot and the environment. And then in this simulation, the system is trained to cope with all anticipated variations, right? So maybe different lengths of the fingers or different grounds. And this works already pretty well, even for quite complicated problems like this in-hand manipulation or quadruped locomotion. And it's really, really remarkable. But there are some problems with this, or potential downsides, namely that I need high fidelity simulations. I need to be able to simulate the system quite accurately in advance. And the learning is so far relatively inefficient because I need domain randomization. I need to essentially simulate everything 100 times for all different possible variations of the system. And then the largest downside, I think, is that the controller that you're getting once you're doing this is essentially fixed. So once you deploy the system, it just sort of runs, and it doesn't really adapt. If it fails, well, it fails. And the other problem is, in principle, if I want to start now to do a new task and I need to start from scratch. So how do we achieve efficient learning and online adaptation in these robotic systems? And so one direction, hopefully, is to use model-based reinforcement learning. And it comes in two different flavors to get you a little bit up to speed. So one option is to use the Bellman operator to optimize the value function and the policy. And so how does that work? The black line here shows, let's say, what our system is doing at the moment before it's learning, and it should maybe approach this dashed line here, let's say. And so I'm using the model, which are indicated here by this little yellow stripes, to indicate what the model would predict if I do some other action. And then I can use these counterfactual simulations essentially to optimize without actually querying the real system. So in this way, I can get faster than running again on the real robot. And that's what I want to avoid, right? I want to be fast in terms of real-time interactions. And so what is cool about this is that I'd have a global optimization. I really find a good policy, but for a very specific task, namely exactly the one that I want to solve. And the second direction is essentially using planning methods to search for a particular policy on the fly. So what does that do? It uses the model to essentially simulate what's going to happen in a longer, or like in a finite horizon step, and then directly executes that. And with this, I can run for a new task immediately. I can sort of think how to do that task, and I can immediately do it. Maybe not as optimal, but I can immediately adapt to a new task. Okay, so and I will talk about this second idea because I think it's pretty interesting. Okay, so in this domain where I use model-based reinforcement learning with planning, I have a couple of challenges. Namely, I need real-time planning, right? I need to be able to crank out a next action fast enough to be in order to react. And the general purpose planners that have been used in the field of model-based RL have been like at least 1 to 2 orders of magnitude too slow. Then I need good models, which also can quantify uncertainties, as you will see later, and I need to be able to deal with safety aspects. And this is work together with my PhD students, Christina, Sebastian, and Marin, and intern Shamburai. Okay, so the method that I will explain to you a little bit is cross-entropy method, which is a very standard sample-based optimization method that was used in this model-based reinforcement learning domain. And it tries to optimize, it's a black box optimization method, and it simply tries to minimize the cost of a certain action sequence and by sampling-based method. And how does it work? Well, you take actions from a distribution, you randomly sample them, roll them out in your simulation, in your mental model, and then you take the best of those, you refit the parameters of this distribution here, and you sample again. Then you do this a couple of times, and after you did this for a few times, you will end up with some decent solution. And then what you do in control, you use model predictive control, meaning you only execute the first action and then you replan. So you do planning for a certain time step, but you only execute one action, then you do this again when you do one step. Okay. Well, and you see already on this jiggering path here that the solutions will probably not be very optimal. And so to give an idea how this could be improved, because we are at the end working with physical systems, right? So imagine our robotic system is simply an integrator. So we can model it as a random walk. Our current state X is simply adding the action, and then we have our new state. So this is also known as a random walk. And if we add Gaussian noise, then we get a Brownian motion. And that is sort of wiggling around a little bit through space like that. Now, what we can do, and that's also shown in nature, that, for instance, birds or other predators, they are not randomly walking around, but they use Levy walks. Namely, their action sequence is not just Gaussian, but it's temporally correlated. And this is called colored noise. And we can quantify this by looking at the power spectrum of this noise. So we take the Fourier transform of the noise sequence and look at it. And so here is frequency, and here is respective power in each of these frequency sort of buckets. And white noise, so the blue line, this Brownian motion is completely flat. So the action sequence in Brownian motion is flat. So all the frequencies are equally important. Whereas if I use colored noise with a certain exponent, that's how they are used, constructed, is then I can, for instance, with beta equals 1, which would be the exponent of this slope here, I can downweight high frequencies and upweight low frequencies. And that's probably something that is good for a robotic system, because if I look now at the random walk, where I use these correlated actions, instead of just wiggling around here very much close to the origin, I can suddenly find really far places in state space. Okay, so now let's put this into our system. So we have developed this improved cross-entropy method, which uses this colored noise, so this power spectral density in this form, and also added some memory to the system that it can memorize what were a good trajectory before, when it was just planning one time step before, and a couple of other small improvements. And so in our cartoonic picture that looks like this now, our action sequences look much more straight, and after the same amount of iterations, I'm hopefully finding a good solution. Okay, fair enough. Let's see how that works when I run this on some real or a simulated system, but non-trivial system. So this is a shadow hand with 25 degrees of freedom. It's supposed to open that door, and I'm getting only a cost function once I open the door. There's no training involved, it's just sampling here. And here you see how that works. It goes for the door, opens it easily with very few samples. And if I give it more, it even starts to hold the door up to make sure that it really stays open. So that's pretty cool. And on the left, you see here the budget, namely the number of samples that I'm using every time step in the planning, and here the success rate. And you see our method here in yellow solves this problem already with 45 samples, whereas the previous state of the art needs about 1,000. So that was really a big success. And this goes on for quite a number of things we tried. So half cheetah is a classical benchmark, or a humanoid stand-up, which is really difficult. Reinforcement learning can typically not solve this. It's about here. It only managed to sit, and we are managing to stand up with about 100 samples per time step. And similarly for the other guys. So let's better look at some of these results here, because they're quite funny to look at. So here first, this hand is catching this ball. You see it opens it, then it is able to catch it in the air, and then it balances on the back because the cost function is such that it should balance it there. We can do this humanoid stand-up, or here another task where such a cube is manipulated and grasped and moved over this. Again, no training involved. It is really just planning out of the box. So this is really remarkable. And I think this is enabling the technology for what we can do next. So we have now this fast planning method, which is generic and can use for arbitrary models and cost functions. And we were pursuing two different things. One is to extract a policy from this, which we can then run very fast on a real system. And the second thing is to learn models and do safety-aware planning. And I will first talk about the extracting the policies. So now we have a method that we can create, where we can create really good solutions for these complicated control problems within a few seconds. But still we need quite some compute at runtime. And also, so far, it was only using ground truth models there in this work at the beginning. So we thought maybe we can use at least this, extract the policy, and then run this on our real robots. And so the goal was to train a policy from this planning data, make the policy and the planner ideally mutually improve themselves, and solve tasks which normal reinforcement learning has hard time to solve. And so maybe let's just do behavioral cloning. This is the term for using the data, training a neural network, and run it on the robot. And if you take this half cheetah running here, you will get quite poor performance. So why is that? Because the problem is that our planning data is multimodal, which means if I have different ways of solving a problem, then my planner will either one time give me this data, next time it gives me this data. So if I train my model, my policy, it will probably just run into this obstacle in this cartoon picture. So, and the other problem is compounding errors. Once I have a policy and I run it on the robot, it might very quickly end up in a situation that it has never seen in the data, so it doesn't really know what to do. So one work that helps here is guided policy search. It's a method that takes our optimization function here, as we had before, but add a term, which means don't be too far away from what a policy would do. So I have a neural network policy, and I can ask it sort of what would that policy do, and I try to make my planner stay close to that. So let's say my policy is not good, but it at least goes on the right side here of this obstacle, then my plan would only take these parts and never give me the other solutions. So this is already better, but still not ideal. So we can already walk forward, but not really fast. And so it turns out there are a couple of problems. One is that our planners is doing some premature convergence. So for instance, here we have a longer obstacle on this side, if you want. Then if my policy goes in this direction, the planner would only look at this data and never actually find the shorter solution. So this is a problem. And still we have this problem of compounding errors. So there was another method out there which is called Dagger, data aggregation. So we essentially asked the planner, once we roll it out, we asked the planner, what should I do here? What should I do here? Should I do here? So that we can ask to improve the situation where the policy really goes. And that is working to some extent, but in our case it wasn't too great, because the planner, if I just ask it for a new state without any history, is not particularly good. It really wants to optimize for several time steps along the path. So Dagger alone didn't do it either on this task. So what we did is we combined these two methods and used an adaptive term here to have this auxiliary cost weighted. So this guidance cost or other costs be auxiliary, because in principle what you want to do, you want to only focus on your main task, and once you can solve the main task to some extent, you would want to look at this auxiliary cost, not the other way around. And so what we do is we compute simply this adaptive lambda here by a ratio between the range of the real cost divided by the range of the auxiliary cost. So this range is simply the max minus the min cost that we have. So imagine now we don't do any progress on the real reward, on the j here. Then this term is 0 and our lambda is 0, so we don't look at this cost. And we really make sure that our optimizer is first trying to find a solution. And once it has a solution, then we look at the auxiliary cost and make sure that our auxiliary costs have a fixed relative importance. So this was really working very well. And when we do this now, we get a pretty decent performance with our method here in blue. And we call this APEX, Adaptive Policy Extraction. Cool. And this also works for other problems like the fetch, pick, and place task, or the humanoid stand-up, or this door opening task. As a really strong part, we can now get policies for pretty complicated problems relatively nicely. The behavior is still not really perfect, and it also has quite some computational cost attached because we need to run this many, many, many times. Okay, now let's look at the second part, namely learning models and do then safety-aware planning. So this was our route to really go onto the real robot. And so what we want to do there is we want to really work on the robots, so we need to adapt to the real system. And the second thing, when we want to work with real robots, we need to worry about safety, right? We don't want the robot to destroy itself or the environment. And the other problem is we really have then runtime constraints. We need to run at least 25 hertz for most systems. And so one of the challenges that we want to solve is we need to explore efficiently, but also carefully. And we need very powerful dynamics models now. Before it was in using simulations, but we want to use now real models of the real robot that we can cope with all the particularities of the robot. And so, and the other thing that we need is to be aware of uncertainties. And so this uncertainty aspect is really important when we run something on the real system. So let me give you a little bit of a primer of the different types of uncertainties that you might encounter and which are important. And so let's assume we have data here. These are the red dots. And now we can look at this and we have a model that needs to make predictions, and there are two types of uncertainties that the model has. One is aleatoric uncertainty, which is essentially inherent to the data, and it's simply the measurement noise or the irreducible noise in the data, right? So we can't do much about it, but we need to know about it, okay? So this is aleatoric uncertainty. And the second one is epistemic uncertainty, comes from knowledge, and it means the uncertainty that I have because I haven't seen any data yet, right? So this is sort of out of distribution detection, if you want. And now, so why do we care? Well, in this model-based reinforcement learning setup, on this control setup, we actually want to avoid aleatoric uncertainty. We want to don't go to places which are just unpredictable, right? And we want to seek epistemic uncertainty to some extent because we want to know what's going to happen there because we need to learn. So in this way, we need to make sure that we can distinguish between the two. But we also need a model that can actually handle those nicely. So here I give you a couple of ideas. If you run now a distributional model that can predict a single distribution, then we can nicely figure out the aleatoric uncertainty, that's fine. But outside of the data, that wouldn't really tell us too much because you still get a single prediction and we don't know what that is. So now taking up this ensemble idea that we had been discussing before, if I take now an ensemble of these neural networks, which are models which are probabilistic as an output, then I get both an aleatoric uncertainty, but also I get epistemic one, namely by the disagreement between these guys. Okay, so what we are doing is we are using an ensemble of deep probabilistic networks, and that is let's say, a decent compromise for these uncertainties, and we can distinguish the two types. Okay, so now this was for one particular step, but now we have in our planning problem, we have many steps that we want to predict, right? Let's say a 30 steps prediction in the future. We want to predict what's going to happen. And so we need to make good predictions over time. And there was a model, there was a paper called Reinforcement Learning in a Handful of Trials, here called PETS, Probabilistic Ensemble Models with Trajectory Sampling. And that worked the following. I have my initial state, then I go to one of these probabilistic networks. This will predict a distribution. I sample from the distribution, and then instead of predicting with the same model more and more, I'm taking this output and going to a randomly different model. So I do particles that essentially go through that ensemble system. And that was shown to be quite powerful. And at the end, I get, again, sort of a distribution of outputs. Fair enough. The problem is that my uncertainties gets mixed up here once I do this one step further. I get here a prediction, but then I lose this differentiation between aleatoric and epistemic uncertainty once I do this n-step prediction. So that's bad. And so in our model here, we take the same idea, but we use essentially two types of particles. Ones do the same thing as before to reduce variance, and the second particles, they go straight through that system and they don't sample, they only take the mean. And so these mean particles, they allow me to, at the end, to cope for to really have only this aleatoric uncertainty, which is here the standard deviation, the mean of these standard deviations. So we look at all of these distributions here, and the mean of these guys is my aleatoric uncertainty. And my epistemic uncertainty is essentially the red particles, and I look at how much do the ensembles disagree, both in terms of their mean and in terms of the standard deviation. Okay, so with this thing, I can now do an n-step prediction, and at the end of this n-step prediction, I have a rough estimate of my aleatoric and epistemic uncertainty. Okay, so now what can I do with this? I can do different things. I can do efficient exploration. Namely, I'm adding an exploration bonus to my cost function. So I'm saying, okay, if you're able to decrease your epistemic uncertainty, that's good, and I have an additional parameter, WE here. And so let's look at this little toy bolt. We have a bridge, a system of bridges here. If I fall down, then I'm in the lava, so that's bad. And here I have three different pathways. One is relatively narrow, and I can fall down. One is the same size, but I have fans which are blowing me off randomly, so this is the sort of the dangerous part. And one that's more safe, but further away. I need to go from here to here. Now, if I'm learning without any bonus, my system will hardly explore any of the other bridges. It will only explore this one and a little bit of this one. So I will probably not have a very good model after I learn this. But if I add this epistemic bonus, I'm very quickly getting exploration of this entire system here. And so the second thing, but I want to do this probably mostly in simulations, of course, because in the real system I would fall off. Now, the second thing I can do is I can do risk-aware planning. Namely, I can make sure I'm not going onto the places where I have high aleatoric uncertainty, so I can't really make sure that I'm getting over. The point is a planner will otherwise just trying to sort of have a lucky run through that, but the real system might be quite harsh. So by doing this, we can now, depending on this additional factor here, we can see how we can avoid falling off. So this is the baseline. Without this additional term, this would have only 60% success rate, and if we choose a decent parameter for this aleatoric penalty, we are reaching 100% here. Okay, and now in a second example, maybe a little bit more illustrative, is the one where I have such a robot, and let's assume I have some measurement noise or some other failure on part of the state space, which is there. So let's say on the left, I have always a noise in my gripper. It opens or closes randomly, and on this side is all is good. And so now, what I would like to see is, of course, that I'm not letting the object fall down. So one strategy would be to push the object to the side where I have no noise, grasp it, and lift it, and that's what our method would do, whereas the baseline method would just try to grasp it because that's the shortest way to go to the goal, and that would likely have failures. So this is what happens here. Depending on this noisiness of the side, you see here the dropping rate of the classical system would be quite high, whereas our system would drop the object much more rarely. Okay, so now that is about these different types of uncertainties, but I can also use them now to make sure my system is not violating any real hard constraints of an unsafe set. So for instance, if I have a definition of a place which I shouldn't go, then I can now say, okay, what is the probability of me hitting that bad area? And then I can define a probabilistic safety, namely because I'm predicting distributions, I can say what is my probability of ending up there. So I have this probabilistic safety constraints delta here. And I can now say, okay, whenever I hit this, then I incur a very high penalty. So this W here would be a high number, high enough to dominate the entire optimization. And here's an example. So we have this 8 degree of freedom robot that is supposed to stand up. And here is an indicator of whether I'm violating the constraints, namely whether my robot touches this fragile object. The front legs of the robot are fixed, so it has to really lean over. So it's not just standing up, but has to lean over, and it's balanced so that it often falls down. So like here you see in this case, it would just fall down and crash into the object, whereas our system here on the left wouldn't do it because it is able to compute that it never really enters the unsafe set. And this is here on the left, you see this in quantified number. So normally you have quite often a safety violation, and then depending on our fraction, whether I want really no safety violation, I'm also getting none, probabilistically, of course, and with I'm allowing some, I will get some safety constraints, some safety violations. So I can really control this now nicely. Okay. So these are our first steps into this direction. And to summarize, we have, I showed you our fast and universal planner, ICM, that works on arbitrary models and cost functions and is like 1 to 2 orders of magnitude faster than what we had before. I showed you how to extract policies from this, and it's quite difficult, but we have some solution. But maybe now offline reinforcement might be a better choice of doing this. And lastly, I've showed you planning with these learned models, and we are really looking forward to apply this to the real robots that we have in the lab, but the pandemic wasn't really helping us here on this. And with this, I'm at the end. I would like to thank my wonderful team, my funding sources, and of course, you for your attention. Thank you so much.